AQA A Level Physics, Radioactive Decay. This big chunk of the specification we're going to get done today, quite mathematical as well. So, imagine you've got a big bucket with lots of dice in it, hundreds of dice in this bucket, and you give the bucket a good shake and you tip all the dice out on the floor. What is the probability that any dice will land on a 6? Think about it, pretty easy. Now, why is it unlikely that exactly 1/6 of the dice will land on a 6? And what else will determine the number of dice that land on a 6? So you've had to think about that, and basically look at this equation here. Now, the number of dice is n, let's say. So that might be 200 or whatever. This thing here is the probability that you will roll a 6. Call it the decay constant, if you like. That's the probability that you will roll a 6 on a particular throw. And in this particular experiment, that equals a 1/6. And then this dn dt is the change in n every throw. And the change in n every throw, so delta n would be the number of dice that you take away, and delta t is just one throw. So we could leave that out because it's per throw. So the number of dice that you take away, the number of dice that you land on a 6, depends on the probability of rolling a 6, and it depends on the number of dice, doesn't it? Now, here's a radioisotope. It contains radioactive atoms, unstable atoms. And every second, a number of atoms will decay, because they're unstable. So they are like dice. An unstable atom is like a dice. And in the next second, it might decay. It might not. It might decay. It's unstable. It's a random process. The number of atoms which decay every second is called the activity. And you could measure it in decays per second. We use becquerel, and a becquerel is a decay per second. And so the activity is the change in n every second. It's the number of decays every second. So the activity is delta n over delta t, or actually dn dt, the number of decays per second. And the activity will depend on two things. It will depend on n, which is the number of atoms in the sample, and it will depend on the probability that an atom will decay in the next second. And so we get this equation here, dn dt equals minus lambda n. dn dt is the rate of change of n. Yes, n is getting smaller as time goes by, and the rate of change of n, how quickly it's getting smaller, is the activity. It's how many decays happen every second, dn dt, how many atoms decay every second. And dn dt, the activity, will depend on two things. It will depend on the decay constant, and there's lambda there, the decay constant, and that is the probability that an atom will decay in a certain time. For example, in the next second. If it's the probability that it will decay in the next second, then the decay constant, its units are seconds to the minus 1. You can actually do any unit of time, but for the probability it will decay in the next second, it's seconds to the minus 1, and n is the number of atoms. So have a go at this question here. Radon 220 has a decay constant of 1.33 times 10 to the minus 2 seconds to the minus 1. a sample contains 12 nanograms, nano is 10 to the minus 9, of radon-220, calculate its activity. So lambda n, lambda we're given. One thing you need to be able to do is to work out how many atoms there are in 12 nanograms of radon-220. Do you reckon you can do that? Well, to do that, you need to understand moles. Okay, 1 mole contains 6.02 times 10 to the 23 atoms, Avogadro's constant. Okay, in physics we say Avogadro's constant, it's n with an A there, and that is 6.02 times 10 to the 23. Now 220 grams of radon-220 is 1 mole. So 12 nanograms will be 12 times 10 to the minus 9 times Avogadro's over 220, which is that many. So that's n. So now that we have n and we know lambda, we just multiply them together and we get the activity. The minus sign is there because it's a decay, because delta n is negative. N is getting smaller, so strictly speaking there should be a minus in there because it's a radioactive decay. dn dt, the gradient of the graph, is negative. So dn dt is minus lambda n. Now this is my differential equation, and the solution to this differential equation is n as a function of time, and there we get this equation here, n equals n naught e to the minus lambda t. Don't worry about anything I've just said. Basically it's another important equation that you need to know, that you need to be able to use. N equals n naught e to the minus lambda t, and it is n as a function of time. So if you plotted n against time, you'd get this very familiar kind of decay, this exponential decay. Now, as the activity dn dt is proportional to n, then the activity against time will also go down exponentially. Here we are, as it does in the specification, instead of dn dt, we're writing A. So A equals A naught, which is the activity at the beginning, times e to the minus lambda t. This e to the minus lambda t, what I find very, very useful, if you think about that, it's the fraction that's remaining after a certain time. So at the beginning, e to the minus lambda t equals 1, and then as time goes by, it gets less and less and less and less, and then eventually it will get to 0. So e to the minus lambda t is the fraction remaining after a certain time. If you multiplied it by 100, it would be the percentage remaining after a certain time. So it starts at 100% and then it gets smaller and smaller and smaller until eventually it's 0. So n equals n naught e to the minus lambda t, a equals a naught e to the minus lambda t. Here's a question for you to do. Strontium-90 has a decay constant of that. A sample contains that many grams of strontium-90. How many atoms does it contain, etc.? What's its activity? What will its activity be after 10 years? How long will it take for its activity to fall to 10% of its original value? See if you can do it by yourself. Pen, paper, calculator. The answers are. Okay, so the first thing that we did was work out n, the same method as before. So 8 times 10 to the minus 12 grams. So 8 times 10 to the minus 12 times Avogadro's over 90, because it's strontium-90, and there's n there. So we've worked out the number of atoms. dn dt, we just multiply by the decay constant. Okay. Now, what will its activity be after 10 years? So what we need to do is in the equation, which is there's e to the minus lambda t, and there's lambda there, 1.1 times 10 to the minus 9, and then we want t in years. Usually on your formula sheet, it tells you how many seconds there are in a year, which is quite useful. And if you work it out properly, you should have got 41.6 becquerel. How long will it take for its activity to fall to 10%? Now, remember that e to the minus lambda t is the fraction remaining. So if e to the minus lambda t is 0.1, because that's 10%. And then what you do is you take logs of both sides. What I tend to do is I flip it. So I say e to the lambda t is 10, and then take logs. So lambda t is log 10, and so t is that many seconds, which is 66.4 years. There is a property of exponential decays, and that is that in equal amounts of time, it will fall by the same fraction. And if that fraction is a half, then we call that amount of time the half-life. So the half-life is the time it takes for the activity to halve, or it's the time it takes for the number of atoms to halve, the number of unstable atoms to halve. The number of daughter atoms will actually be getting bigger, by the way, but the number of unstable parent atoms will be getting smaller and smaller, and the half-life is the time it takes for n to halve, or the time it takes for dn dt to halve. And it's very useful knowing the half-life, okay, for obvious reasons, I think. How do we work out the half-life? Well, in my equation, A is A naught e to the minus lambda t. If it's the half-life, then A over A naught is a half. So e to the minus lambda t is 0.5. So e to the lambda t is 2. So the half-life is log 2 over lambda. So that's a very useful equation. The half-life is log 2 over lambda, or lambda is log 2 over the half-life. Have a go at this. Pen, paper, calculator, and I will show you the answer now. The first bit, there's something you should always look out for. If you're given an activity and you're given a time, is the time a multiple of half-lives? This especially happens on multiple choice questions. We've got a half-life of 25 minutes, and it says, what will the activity be after 50 minutes? Well, that's 2 half-lives. So the activity will halve and then halve again. So it'll go from 800 to 400 and then 400 to 200. So just in my head, I've worked out the activity is 200 becquerel. So keep an eye out for that. Is the time a multiple of half-lives? For the second bit, the time is not a multiple of half-lives. So what you need to do is work out the decay constant from the half-life, and then use A equals A naught e to the minus lambda t. And if you've done that correctly, you should have got 606 becquerel. More about half-life. Now, carbon dating. Living things contain a lot of carbon, and a small fraction of that, I think it's something like 1 in 10 to the 14 of the atoms, is carbon 14. It's a very, very small fraction of the atoms. I can't actually remember what it is. Now, when a living thing dies, this fraction will fall because the carbon 14 atoms decay, and so there are less and less carbon 14 atoms. And so you can use that to date remains, for example, this skeleton. Carbon 14 has a half-life of 5,730 years. So a sample of bone from an old skeleton produces a count rate of 10 counts per minute. The same mass of a new bone produces 14 counts per minute. Calculate the age of the bone. Discuss the limitations of this technique. So e to the minus lambda t, remember that's the fraction that's left. And this is how I've done it. I've said that e to the minus lambda t is 10 over 14. And if you do that, you get 2,780 years. The limitations of the technique, well, one thing is we are dealing with very small amounts of radiation. So you've really got to shield from background radiation very carefully. Also, the bones may be contaminated with other radioactive stuff. Even just handling the bones, you may be putting some radioactive material on them. If the amount of time involved is short, if it's like less than 500 years, then the activity won't have changed very much. Look at the half-life. In 500 years, that won't have gone down very much. Also, if the age is, if it's very old, if it's like 50,000 years, then the amount of carbon-14 left in the material will be very, very small. So basically, there are limits to the time frame that you can use this technique. But carbon dating has turned out to be very, very useful. In a medical context, I think I might have mentioned this in my last video. If you're doing like medical imaging, you want something with a half-life of about 6 hours. Technetium-99 or technetium-99 has a half-life of 6 hours and gives off gamma. Why does that make it a suitable isotope? Well, one thing is it gives off gamma, so you can detect it outside the body. The other thing is, because its half-life is 6 hours, after a couple of days, there won't be very much left, because while it's in the body, it's doing damage. So you don't want it to hang around. You want it to do its job, do your medical imaging, and then go away. So a half-life of about 6 hours is good. How would you actually go about getting the half-life? Well, you could do a graph of count rate against time. One thing I will say here, by the way, count rate is not activity. If you've got a lump of radioactive stuff and there's lots and lots of decays happening there and it's emitting lots and lots of particles, let's say it's giving off beta particles, then if I put my Geiger-Müller tube there, then it's not going to detect all of the beta particles. It'll only detect a fraction of them. So what it detects is the count rate, which is going to be a lot smaller than the activity. In fact, a lot of the beta particles won't even escape from the material. So when we say count rate, that's not activity, but it will be proportional to the activity, so we can use it to find the half-life. If you're lucky, you might have seen this experiment done, which is getting the half-life of protactinium. Now, you can get the half-life off your count rate against time graph. You know, if you start there and then the time it takes to get to a half, and then you do that 3 times on the same graph and take an average. A better way is if you actually plot the natural log of the count rate against time, and if it's an exponential decay, you get a straight line. You do a line of best fit. The points don't fit the line perfectly because decay is a random process. You know, you can't predict exactly how many decays will happen every second, but you do a line of best fit, and then the gradient of this line is minus lambda. If you look at this equation here, when you've taken your logs, log n, or log of the activity, or log of the count rate, is minus lambda t times log of the initial count rate. So y equals mx plus c, the gradient is minus lambda. And that's the most accurate way of getting a value for lambda, and then you can work out the half-life from that. Okay, I'm going to have a little rant now. Now, some of the nuclear waste we have produced and are producing now contains stuff which has a very, very long half-life. Some of the isotopes of plutonium in the waste, that's got a half-life of about 200,000 years. Very, very long half-lives, many thousands of years. And it is useless. And it is very, very, very toxic. You know, it's very carcinogenic. It is terrible. and you've got to stop it leaking into the environment. Okay, you can't do what a certain country did and just sink its nuclear submarines in the Baltic when they got too old. You have to look after it. You've got to guard it from terrorists as well. Okay, if it leaks into the environment, then the results would be catastrophic. Now, no matter what we do, future generations are going to have to deal with this. They're going to have to deal with the problem. They're going to have to look after our rubbish for thousands and thousands of years. And it will be a big problem for them, and it will cost them an awful lot of money. What a waste. You know, if we can get nuclear fusion working, then why are we doing all this nuclear fission now? We've got wind power is cheaper now. What is the point? I don't understand. It's a very NIMBY attitudes. Now, does our government have a good strategy for dealing with nuclear waste? And the answer is no. Their strategy is put it in a big pile and we'll sort it out later. Some future government, and whether it's a Labour or a Conservative government, they just haven't been dealing with this problem. And it's going to be a big, big problem for future generations. A little quiz question for you. One of the first nuclear power stations in this country was Sellafield. How much is it going to cost to decommission it? In other words, to knock it down and then look after all the bricks and all the bits of low-level waste and medium and high-level waste. How much is it going to cost to decommission it? And the answer is, the latest estimate is £110 billion. And just imagine if that money had been invested in renewables, you know, we wouldn't need nuclear power. Do you get the feeling I'm a little bit anti-nuclear power? Do you reckon? Well, because I am.